In the next section, we're going to work with the dot product. And the dot product is a number, a scalar, if you will, that is useful in certain applications. So when we find the dot product, it's pretty simple. You just you take two vectors and you multiply their corresponding components and add up the results. So it's really important to understand that the dot product of two vectors is a scalar and not a vector. So let's go ahead and do a couple of examples. So for part A here, u dot v will just be 3 times 4 plus negative 2 times 5. So 12 minus 10 is 2. B, u dot v, 2 times 5 plus 1 times negative 6. 10 minus 6 is 4. And you can also take, this isn't an example here, but say I use from example A, u is 3, negative 2. So, and I ask you to find u dot u. So you can take the dot product of a vector with itself, is what I'm saying. So 3 times 3 is 9. Negative 2 times negative 2 is 4. And we would get 13. Now all of these happen to have a positive result, but the dot product can be negative, it can be 0. The key thing to remember is a real number. It's not a vector. Okay, here are some properties of the dot product. It's commutative, so it doesn't matter which order we multiply the components in, add the results. If we take a scalar times a vector and then dot with another vector, we'll get the same result as if we took that scalar times the other vector first and then took the dot product. So that's an associative property. Here, this of course is a vector u plus v, then dot that result with w. So this is a dot, not multiplication, right? Or we can basically distribute. This is a distributive property. We'll get the same result if we do u dot w, which gives us a real number, plus v dot w is a real number, and add up those numbers. We're not going to prove that, but you could prove that pretty easily. And then here, the magnitude of vector u squared is u dot u. So of course here we can do it with this one quick because we found u dot u is 13. The magnitude of u would be the square root of 9 plus 4. So if you square that, you'll get 13. That's pretty easy to show. 5, this is the 0 vector. When you dot that with u, vector u, no matter what u is, of course, you're going to get 0. You'll just get 0 plus 0 equals 0. So this is a real number, this is a vector. Okay, so a little bit of terminology here on the bottom of the page. If we're talking about the angle between two vectors, u and v, we're talking about the acute angle in between the vectors. So I'll call this theta. Maybe this is vector v and this is vector u. Then theta is 0 or pi. Then we say that these two vectors are parallel. So that would give us, either u runs with v or u runs the opposite, right? That's what this is saying. Then those are parallel vectors. And if theta is pi over 2 or 90 degrees, whoops, that's a right angle, of course. If that is perpendicular, if these vectors are perpendicular to each other, we use the term orthogonal. These are orthogonal vectors here. Whoops, orthog. Lost track of where I was. So if they lie at a right angle to each other, then they're orthogonal. All right. So we're not going to prove this theorem either, but there is a proof in the textbook if you are interested in it. But we can show that when you take the dot product of two vectors, you, of course that's a scalar, right? You'll get the same result if you take the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle in between the two vectors. So again, theta is between, if this is u and this is v. Oops. So you want to use, don't use this angle. It's the angle between 0 and pi, or 0 degrees and 180 degrees if it's in degrees. Oops, excuse me. Okay, well this naturally implies this. If you divide both sides by the product of these magnitudes, you get cosine of theta is u dot v over the magnitude of u times the magnitude of v. So this, if we solve this for theta, that gives us a formula for the angle between the two vectors. Of course, theta would be the cosine inverse of this number. So let's go ahead and do an example of that. We want to find the angle between these two vectors. And let's draw a picture as well, so we just kind of get a sense for what we're really doing. So we have 2, 5. Right, so this is vector u. And then v is 4, -3. So we're looking for this angle here, theta. Okay, well we know the cosine of theta, using the formula right here, is u dot v over the magnitude of u times the magnitude of v. Whoops, this should be bold in here. So in this up here, this is dot product, and then this, should have put a bigger dot in there. This is multiplication down here, right? Okay, so u dot v is 2 times 4, which is 8, plus 5 times -3, which is -15. The magnitude of u is the square root of 4 plus 25. And the magnitude of v is the square root of 16 plus 9. So we get -7 over square root of 29 times 5. I'm going to put the 5 out front. Right? 16 plus 9 is 25. So square root of 5. So that implies theta will equal the cosine inverse of -7 over 5 square root of 29. And the nice thing about the cosine inverse function is if this is a positive, it'll give us an angle between 0 and 90, or 0 and pi over 2. And if this is a negative, it'll give us an angle between 90 and 180 degrees. So I think I need to change back. I was working in radians last time. Yep. Okay, so I'm going to use degrees, but you could, of course, use radians. So cosine inverse of -7 divided by 5 radical 29. It's approximately 105.1 degrees. And that seems reasonable from our little picture, little sketch here. This looks more than 90 degrees. Okay, then our next theorem says that two vectors are orthogonal if and only if u dot v equals 0. So if you look at our formula, u dot v equals magnitude of u times magnitude of v times the cosine of theta. It makes sense that, if this is orthogonal, this would have to be 90 degrees. And cosine of 90 degrees, 90 degrees is equal to 0, of course. So if this is 90 degrees, the 0, so u dot v is 0. the if and only if means we can go both directions. So if we know theta is 90 degrees, then u dot v is 0. If we know u dot v is 0, then we conclude that theta is 90 degrees because cosine inverse is 0 would be 90 degrees. So this goes both directions. You can't have one without the other. So in part A of this next example, just real quick, if you want to know if these are orthogonal, you just find u dot v. 3 times 2 is 6, plus 5 times negative 8 is negative 40. So negative 34, that's not 0, so no. That's all you need to do to determine if the two vectors are orthogonal. B, u dot v is 2 times negative 1, which is negative 2, plus 1 times 2 is 2. That equals 0. So yes, those ones are orthogonal. All right, so another place we use the dot product is when dealing with this, what's called the projection of u onto v. So let's draw a picture here to show you the setup. So we have two vectors. I'm going to put v along the x-axis here, but it doesn't have to be. Just makes our diagram a little easier. So here's v, here's u. So the projection of u onto v, imagine if there's maybe the sun is up here shining straight down to here, so that this is a right angle. This vector right here is the projection of u onto v. So the onto part is down here. It's easy to mix up like which one is which. The projection of u onto v. Okay. So the reason I drew it, if this, any two vectors, if this is v and this is u, just kind of imagine if I turn my page this way, this is a right angle. What did I say here? This is v, this is u. This would be projection of u onto v. If I call this u and this v, I'm going to write projection of v onto u. Maybe I'll use some different vectors. So maybe this is w and this is u. Oh, let's call this one v. And then this vector here is the projection of v onto w. Okay, so it's important you get those in the right spot. Okay, and we always have this right angle, so it's like coming straight down and forming a right angle onto the vector. So it's like a shadow, it's casting this shadow, right? Okay, so the reason I drew it in standard position here is because we can figure out how long this vector is, the length of this vector. So here's our vector. We'll have the same, will be the length of the horizontal component of vector u, right? Vector u is the magnitude of u cosine theta. Well, excuse me, I'm writing ordered pairs, that's the ordered pair here. But these would be the components of vector u as well. Vector u, or magnitude of vector u, sine theta, right? And this is theta, of course. So this length here, that is the horizontal component. Of vector u. So we just get that from there. These are the same length. Notice these are lengths. So this is a magnitude, not the actual vector. Now we just bring in, this is a number, so it's just this number times this number times this number divided by this number. So this is equal to this, of course, because these would give us 1. And then this part up here, by definition, is equal to the, well, not by definition, but we could prove it as a theorem, right? From back here that sorry, I lost my train of thought, that this is equal to the dot product, u dot b. There it is. Okay, so this is the magnitude, well, here I have it right here, magnitude of projection u onto v. That's how you find that if you don't know what theta is. If you know what theta is, you can just use that formula. So u dot v divided by the magnitude of u. So now, how do we find the actual vector? And of course, if it were actually on the x-axis, it would just be, you know, this would be the first component and then 0 would be the second, but that's not always the case. So it's going to run parallel to vector v. Notice that. So we're going to take the magnitude of the projection of u onto v times, this is a unit vector in the same direction as v. And that gives us this formula. So there's our u dot v, there's our v. So that's what makes this a vector, right? We're multiplying by a vector. This is all a scalar. And so magnitude of v times magnitude of v is magnitude of v squared. That's our formula. So let's go ahead and do an example. So if u is I plus 4j, v is negative 2i plus j, find the vector projection of u onto v. So again, this is a vector projection of u onto v. So u onto v equals, so we do u dot v, so 1 times negative 2 is negative 2 plus 4 times 1 is 4 over the magnitude of v squared. So I'm pointing over here, but I'm actually using this. Magnitude of v squared. So, you know, excuse me, just drop the square root. So it's negative 2 times negative 2 is 4 plus 1 times 1 is 1. And then you just multiply it times vector v for this last part, negative 2i plus j. So see, that's our scalar and that's our vector. So we get 2/5 times negative 2i plus j, which is negative 4/5 I plus 2/5 j. There's our answer. So again, what does this mean? It's good to draw pictures and think about what's happening. Let me draw a diagram. We have 1, 2, 3, 4. Here's u. V is negative 2, 1. We're casting this shadow, and this vector right here is negative 4/5 I plus 2/5 j. That's our projection vector. All right, what do we got? Oh, okay. So now what we're going to do, if I can just use this diagram here, we are going to decompose vector u into the projection vector plus this vector here. If we add these two vectors here together, we get u. So if we find the projection vector and we know vector u, all we have to do is subtract u minus the projection vector to get the other vector. Okay, so these are the vector components of v. I think I changed notation. V. That's okay. We can deal with that. So I use vector v here instead of vector u. So we have two non-zero vectors. Vector v can be expressed as the sum of two orthogonal vectors. So notice in my diagram, these are at a right angle. That's why they're orthogonal. So we have this, the first one's going to be the projection vector. The second one we're going to find using subtraction. So here, that's what I did, right? I said the first one's going to be the projection. So we are projecting, wait a minute. I got some notation issues here. I've got a typo. Let me think about this for a second. Oh no, wait. Oh, I know what I did. Okay. I wanted to change it in terms of v and w, which I did here, but I forgot to change it up here. So this v, I'm doing projection of w onto v. Okay, so I'm going to just change u. This v is the same. I'm sorry about that. Oh, I don't know why I did that. I should have just left it as it was. Okay, so projection of v onto w. Yes, that's right. Okay, so what we have let's say this is w, and then maybe this is vector v. So the oh, I got these backwards. Grr. Well, actually, it doesn't matter. I'll just leave it like that. I'll just project the other way. So I want to project v onto w, so I was thinking about going like this, but I'll just go like this instead. Doesn't matter. Can work with this, right? So this is my first vector. I'm calling v1. That's the projection of v onto w. Then the second vector is actually here. This is v2, and it's going to be v minus v1. So if you notice, if you go back here, minus v1, you would get the same vector right here. So once you find the projection, all you have to do is subtract. Okay, w and v. Okay, I'm thinking w, projection of v onto w. Okay, yeah, I think I wanted to change it because I used different notation here, but it doesn't matter. You should be able to replace the letters. Just, you know, if you understand the concept, you should be able to get the letters in the right place. Okay, so here we have v is, and I'm going to draw a picture again to make sure we understand what's going on. Let me change pencils. So v is 1, 2, 3, 4. Here's v. W, oh, this is the same one, isn't it? Sorry. Well, that's okay. We're still going to draw a picture. Here's w. So we, is this, sorry, I should have looked these notes over before I started this because I'm kind of messing, just blabbing. I can't even find my page. Is this it? Nope. I'm looking for that other diagram I already drew. Oh, it's on the back of this. No wonder I can't find it. Oh, I called it U and V here. Yeah, see, I tried to change the notation quick before I posted these notes for you guys, and I forgot I wasn't consistent and I didn't change it throughout. So I called it U and V here. So why they the same? Yeah. I wish I would have left things alone. So let's leave this as u and this is v. Find the decomposition of vector u into vectors v1 and v2 where v1 is parallel to v and v2 is orthogonal to v. Okay, so we already drew this picture once, but we were talking about, so now I relabeled, right? This was u and this was v. Okay. So we already found v1 on the previous page. v1 is the projection of u onto v, which is negative 4/5 I plus 2/5 j. Okay, so that's our first vector. Now v2 is u minus v1. Okay, I used v's over here, but that's okay. So u is I plus 4j. Being sloppy. I'm getting tired too. I plus 4j minus v1 is our projection vector. So if we want these two to add up to this, we can just subtract this from this to see what our result is, right? So we end up with sorry, 1 plus 4/5 I plus 4 minus 2/5 j. So 5/5 plus 4/5 is 9/5 I. And then this is 10/5 minus 2 is 8/5 j. What was I gonna say? Oh, did I just say 10/5? That's 20/5. That's 18. Okay. Oh, I know what I was gonna say. So that's this vector, and keep in mind that's not in standard position, right? So you would draw it over here. Actually, that's our 9/5 plus 18/5 j. And if this were graphed more carefully on a grid, it would look, this looks close to 2. I'm a little off probably in my diagram. But you get the idea. So here's v1, here's v2, and if we want to check and make sure that these are actually orthogonal, we find the dot product. So check v1 dot v2, making sure they're orthogonal. Negative 4/5 times 9/5 plus 2/5 times 18/5, and this is a good check, especially like I made that mistake. I would have figured out I did something wrong. So negative 36/25 plus 36/25 equals 0. Make sure I got this on screen. There, I do. Okay, so I feel good about our answer then. All right, another place we can use the dot product is in some problems with dealing with work. I'm going to take a break now because I'm really tired and I didn't do the best job on that problem. I apologize. But when you are doing this, it gets confusing with all the letters, like keeping straight what goes where. So that's where it helps to remember, like when you say it, projection of u onto v or projection of v onto w, kind of follow that pattern. And then v dot w, my notation here, there should be a w. you're projecting onto, oh, where is that thing? Here it is. The vector you're projecting onto goes down here, okay? And the vector you're projecting onto is the vector you multiply by. So this here goes here and here, and then this is our u dot v. So if they're different letters, then you can get them in the right spot. If this is a w, then these are your w's, right? And of course these, you have one of each. I don't want to confuse that. The picture helps me, because I obviously had a little trouble there with what goes where. That's when I looked to the picture. And I remember, oh yeah, my vector has to go this direction. That's the vector that has to go here then. Okay. Well, I'm going to stop the video now, and then we'll pick up with work later.